So cool. Yeah. My name's John Singleton. I am COO and co-founder of watchful.io. We're going to be talking about a new data structure or data pipeline structure called Stream Filter Drain, or SFD. So first off, little thanks. Thanks to Compose.io for hosting DataLayer. For anybody out of town, welcome to Austin. It's a great place. I've been here on and off for the better part of about 10 years. And also thank you to JP Rangaswamy. He's the Chief Data Officer of Deutsche Bank, as well as Head of Strategy and Innovation. Highly suggest check out his blog posts. We actually stole the Stream Filter Drain title from one of his blog posts called Filtering the Seven Principles. Incredibly prescient about data, data flow, fire hoses, and the concept of filtering. So that's me, obviously, and my co-founder, Cheyenne. So I'll give you a little anecdote here. At RSA, talking to a senior engineer at a large tech company. By the end of it, he goes, "Oh man, I thought you were an engineer." I said, "No, I'm not, but that's the biggest compliment I've ever received." And he goes, "Yeah, I absolutely hate seeing some asshole in a sports coat who doesn't know what he's talking about." I said, "Well, I'm just showing a picture of me in a sports coat, so probably not too good for the developers here, but I will be the first to tell you that I don't know what I talk when and when I do know what I'm talking about." So any technical questions, please shoot out to Cheyenne. He'd be happy to answer them. So what are we going to go over? What is SFD and why do we care? How does Watchful enable SFD data pipelines? And a little bit about Watchful Stack and how it works. So what is SFD? SFD is an alternative to traditional ETL data pipelines and processes that enable real-time applications take advantage of the deluge of data efficiently by allowing applications to consume only the data that is relevant to it, in addition to taking advantage of the many benefits of microservice-based architectures. I normally hate when people read directly off slides, so sorry about that. So this is a problem I think we all know quite well, and why a lot of us have jobs here in this room. More data equals more problems. It's difficult to get signal to noise. We're needing to find all the different needles in an ever-increasingly larger haystack. Processing time with that amount of data. Traditional batch processing in ETL, we're dealing with being reactive instead of proactive, or processing at ingest. And the responsibility, scaling to that amount of data in an effective manner is just time consuming and difficult. So we see a shift, big versus fast. We're not thinking about gigabytes, terabytes, or petabytes, but instead megabits per second, gigabits per minute, and terabits per hour. And why this is important, data is fast before it's big. If we look at the data value chain, an individual piece of data, it's its absolute most valuable or reactionary the second it hits our pipe. As it ages, we either did or did not do something with it. But in converse, the aggregate data rises in value as we can do long tail analysis, predictive analytics. So that's kind of seeing that shift of fast data versus big data. And so how does that play into Watchful and this SFD data pipeline? So what Watchful is an easy-to-use, massively scalable, real-time event processor that makes building efficient, fast, and resilient SFD pipelines easy. So don't worry, this will blow up on each piece. So looking at the left here, we have our data producers. As an example, we have a firewall, we have log data, user actions, this could be installed apps, or if you prefer living in the terminal and doing a standard out, we provide a binary to do that called watchful relay. It's like netcat. And we enforce a very simple data structure or data schema. It's just two columns: meta, which is a user-defined JSON blob, which can be of arbitrary complexity, and then content, which is just the string of the content. We make no assumptions about the upstream data. We can ingest structured or unstructured, and meta is not required. It can be passed in as empty, and you're just simply filtering on the string or the content that you're bringing in. So where we sit, this is the filtering piece. Filters are grammar-restricted regular expressions. I believe it was someone said earlier that why is regular expressions ever existing in production? Well, we hope to make regular expressions much faster and easier, and we'll get into a little bit of how we do that later. So we take the data on ingest. It's just going to be a RESTful API ingest. Our core, which is going to handle the filtering, built-in closure. Our engine is built on Rust. That's a little bit of our secret sauce. We have what's called a highly optimized DFA pattern matching engine. We'll get into that a little bit. We use memSQL as a fast caching layer for a time period. The default is 24 hours, but depending on the use case, you can change that. And then everything's going to disk with Postgres. We got definitely jacked up by JD's talk about Postgres and how great it is. And then a closure web tier. With each one of these pieces being horizontally scalable, maybe not to ad infinitum, but to a very large degree, to handle a particular use case and to keep up with real-time guarantees, or whatever real-time means to you for your particular use case. It's important to note that this is content-based filtration without an assumption, or if maybe you don't know what exactly the data that you're looking at that hits your pipeline. You can simply separate it out in real time as it happens. So then going into the drain, we operate on a pull model. So here's a few examples of some API requests. We can either pull, like the first one, we're looking at matches. That's going to be anything that contains the meta that we defined on that first one. We tagged it with the key, tag, and then the value firewall. This could match across multiple different filters that you have, but we're only with anything of those filters that have been tagged firewall at the stream level will get pulled into that match. Also, we could do based on a filter ID that also contains firewall, so we're only matching for one particular filter. This could be something like, quote-unquote evils, generally patterned from regex, something that we're not looking for, or that we hope to not find. We can also tag that with firewall. Something broadly like contains keys email, or just anything that a filter matched based on the content without respect to the meta that it contained. We can throw that down to whatever data consumer and drain it into a traditional monolithic application, a microservice, something like Spark or Storm, a complex event processor, dump it all into Hadoop, figure out what to do with it later. The goal here is to, basically we can mix and match the data that we're bringing in. We basically built a data spine. You can bring in multiple disparate streams of information, fast-moving, dense streams of information. This is designed for hundreds of thousands, millions of events per second of relatively large size, and we can get into specifics of that later. But now we have effectively one source of truth to move data at speed and scale. A little bit about the API, just the Swagger UI. Filters, the important thing to note here is that the filters, your regex, can be edited, and deleted as the stream's running, and with guaranteed memory safety. You can automate a process, like an example would be, we've worked with some managed security service providers. They're monitoring open source intelligence feeds like pastebin.com, GitHub gists. If @company.com shows up in pastebin.com, it may be a false positive. It may not be a data breach. But if @company.com plus the password format plus something else as an identifier of that company's particular information that they're worried about, you could now automate, send user password reset, all just through a tiny 30 or 40 line Python script. And then also our matches, obviously with our API requests, and we'll look at that in a little bit more detail. So the goal here is to be as simple as possible for the maximum amount of flexibility. We can either look at equals meta, and again, so how intelligent or how clever you are with your meta tags. You can effectively split these streams into an arbitrary level of finiteness. Contains that meta, has keys, and then also all of this data that comes in is time-stamped time series data. So we can request a certain window of time to pull from, and then obviously like a limit on the amount of matches that we're going to pull back from there. So I told you when I don't know what I'm talking about, I can tell you exactly what we use. If the question is, why did you use memSQL versus VaultDB or Kubernetes versus Mesos? That's not the question for me, but I'm happy to tell you a little bit about what we do. Built on a Kafka backbone for the scalability, the distributed deployment, and strong persistence. Deploy on Docker images for just the ease of the on-premise deployments and orchestration by Kubernetes for those images for just the resiliency and the ease of management. memSQL, as I mentioned earlier, is our fast caching layer. My favorite part about all this is I learned what the Apache Zookeeper logo was. That is actually what I assume to be a zookeeper with a shovel. I think he shovels shit, but go Apache, please change your logo. Yeah, and the core of the application is built on Clojure and Rust, concurrency, memory safety, and just developer productivity. Rust allowed us to do a lot of cool things, which we'll get into here now with our real-time pattern matching. So how can we do this versus, why don't we just use pcree or something like Google's RE2 for regular expression matching? We built a proprietary optimized DFA, or definite finite automaton, pattern matching engine. It's ultra high throughput. We've tested for low-level network traffic at 160 gigabits per second, but of course that's in some clean room with chicken blood and a prayer said before that. So use cases do change. Real-world scenarios are different. It can hit 160. Let's just say that. But the cool thing is that we can do hundreds of thousands, quote unquote, millions of expressions, considering you have both the money and resources to do that to still keep your real-time guarantees. Traditional regular expression implementations are done in a series. For example, we're doing an experiment with Los Alamos National Labs. They have approximately 8 billion tweets. They're running about 1,000 regular expressions for this particular experiment. Their implementation, in the naive way, is 8 trillion passes on that information. They're running it on a supercomputer in about 12 hours, and we're at worst halving that because we're able to run all 1,000 in parallel for each event. So it's only 8 billion passes on that same 8 billion tweets in just a highly optimized way. Think about, it's kind of a picture of a graph structure if you guys don't know a whole lot about regular expression pattern matching. It's really interesting stuff, let me tell you, but effectively we're applying the whole graph structure of all 1,000 or however many patterns you're searching for all at once. And the kind of cool thing is for whatever your regular expression implementation you're using now, we're very comfortable in saying we're at the very minimum going to be 1.5 to 2x speed up compared to your current implementation. And that only gets further and further away as you start talking about multi-expression matching. Searching for one pattern is not that difficult, and to be honest, we're not going to be that much faster than RE2, but try searching for 10, 100, 1,000 patterns, and I assure you we're going to be quite a bit faster. And a little bit, really, again, exciting pattern matching stuff, kind of talking about NFA versus DFA. NFA is that naive implementation running in a series. You're simply searching for the single graph structure of all those patterns in one pass over and over and over again for every single possible match. DFA, so NFA is going to be extremely compute efficient, but the processing efficiency and time, we deal from an exponential blow up. It's going to take forever. DFA, we gain processing efficiency, but not as efficient as we could be, but we lose that compute. We're basically going to be throwing resources upon resources on it. And there we sit, of course, we made this graph with the optimized DFA in the upper right quadrant. For almost any multi-expression software-based pattern matching, we're going to be as efficient as more efficient and quicker. So why watchful for SFD? Regex filters, you're going to decrease your computing footprint for any current regular expression implementation you're using, and then you're going to double the speed. There are hardware, like ASIC-based pattern matching, but that fundamentally lacks software scale. By Dockerizing the engine and then the orchestration through Kubernetes, we can scale that quote-unquote arbitrarily, but to a very, very large degree. Again, we're designed for millions of events per second and still keeping our real-time guarantees in the the low mid double digit millisecond latencies, and then again, depending on like what real time means to you, we can scale that up or down. Engineer to analyst, or in reality, senior engineer to junior engineer, using RESTful API calls. You don't have to be a distributed systems expert or a pattern matching expert to be able to handle an enormous amount of data and create a very powerful and flexible data backbone for your application or applications. And really, in the marketing words, we make big data fast. And you can take advantage of fast data without having to spend a fortune internally on R&D and your developer cycles to build those. It's turnkey, it's buy versus build. And in theory, we just do one thing, and we do one thing extremely well, and that's going to be real-time filtration of data. So kind of just a few words about what you can build on top of Watchful in this with this SFD pattern. And the most fun that we found is SIM license reduction. Everyone likes Splunk. No one likes paying for it. Letting Splunk sit on or letting Watchful sit on top of Splunk as a pre-filter, basically sending quote unquote only needles, as was said earlier today, to Splunk. It does two things. One, or insert consumption-based SIM here. It doesn't have to be Splunk. You pay based on the gigabyte of logs you hit that hits your Splunk license. Most use cases, we can cut down the log messages hitting your license by 50%, up to 95%. The reality is somewhere in between, and again, depending on use case. Working with several intelligence agencies for signals intelligence, just taking in large amounts of social data, applying. As I said earlier, evil, quote unquote, is patterned in regular expressions often. You're looking for a lot of different types of evil all at once, and we provide a platform to enable the real-time detection of that. A backbone for microservice architectures, real-time fraud detection, and then what we're doing with Los Alamos Labs right now is a massive data set analysis. We just don't do fast data, taking advantage of the very fast pattern matching engine. We're able to reduce their time for a variety of text-based analytics quite significantly. And so yeah, that's Watchful.io. We help make your big data fast, and we hope that take something away from this SFD architecture. The big dream is that we can cut down compute costs by 2 to 10x by simply just delivering data to applications that the applications care about. Instead of having to take in the full deluge or do a scan, we've gotten very good at indexing. But if we can cut that down, we can make these apps both fast and big. So yeah, that's it.